Welcome to the video lecture on optimization problems. Optimization problems are going to be word problems where you are trying to maximize or minimize a certain quantity. So here's our strategy for completing optimization problems. Number one, read the problem carefully and make a drawing if necessary. Number two, label all your variables, noting what varies and what stays fixed. Number three, translate the problem into an objective function, which is going to be whatever quantity needs to be maximized or minimized. You may also need a constraint equation, which is going to be a quantity that stays fixed in the problem. Number four, use the constraint equation to solve for a variable and rewrite the objective equation only in terms of one variable. Number five, maximize or minimize the objective by setting the derivative to 0 or d/e. And number six, verify that a max or min has been achieved. So let's work through these strategies using the next example. Here we have a rancher who has 200 feet of fencing with which to enclose two adjacent rectangular corrals. What dimensions should be used so that the enclosed area will be maximum? So here drawing a picture is very important. So let's draw our corrals. We have 200 feet of fencing to enclose two adjacent rectangular corrals. So you're going to have one big rectangle split into two corrals so that they're adjacent, just like this. Now in terms of variables, we have some different dimensions here that we want to talk about. We've got these widths going across here, and they're all the same, so I'm going to call each one of them y. And then you kind of have your choice if you wanted to call this entire length x, or you could call each individual piece x. And that's up to you how you decide to do it. I'm going to choose to do it this way so that I have equal pieces. Okay, so now what I'm going to set up are my two equations. Now remember, one of these is the objective, and that's the thing that you want to maximize or minimize. So if you read the question carefully, it'll tell you what quantity it is that you're trying to find the maximum or the minimum of. And if we look at this last sentence, it says what dimensions should be used so that the enclosed area will be maximum. So we want maximum area. So if this is my shape, a big rectangle, what would be the formula for the area of this rectangle? Well, area of a rectangle is length times width. This length, since I chose to do each individual piece here as an x, would be x plus x, or 2x, and the width is this y. So my formula for the area of this diagram would be 2x times y. Then we have something called your constraint. So this that we just found, this is called your objective function. That's what you're trying to maximize or minimize. And then we're going to come up with something called our constraint. Now this is the thing that needs to be fixed in the problem. And usually when you're reading these problems, if they give you a certain number or value that you need to maintain in the problem, that's your constraint. So here we have 200 feet of fencing. That is going to be our constraint. We can't exceed that amount. And if you think about what the fencing represents in this picture, the fencing is very similar to the perimeter, except it would also include this middle piece of fencing as well. So our 200 feet is the perimeter all the way around, together with this inside section of fence. So if we add up all those lengths, what formula would that give me? Well, I would have 4 x's and 3 y's. So I need 4 x's plus 3 y's, and that has to be no more than 200 feet. Okay? So when we take a look at our two equations, our objective function isn't set equal to anything. It just kind of represents a quantity. In this example, that's area. And that's what we want to maximize. And what we know in calculus is that if something is going to have a maximum, the only place it can have a maximum is at critical points. And critical points are places where the derivative is either 0 or d/e. So to find out where these maximums might occur, we're going to need to take the derivative of this area function. Now, unfortunately, there's too many variables in this 2xy for us to take a derivative right away. So that's where the constraint comes in. We're going to use the constraint to solve this for either x or y, whichever one is easier, so that we can then substitute in that expression into our objective function up here and eliminate one of the variables. So if we take a look at our constraint, it will be probably equally easy to solve for either x or y. So I'm going to go ahead and solve for y by subtracting that 4x over to the other side, and then I'm going to divide every single term by 3. So my y is 200 thirds minus 4 thirds x, and I'm just going to put a box around that because we're going to be using that again later on. And now what we're going to do with this y expression is we're going to substitute it into our area function to eliminate the y variable completely. So this new area becomes, instead of 2xy, it becomes 2x times this quantity 200 over 3 minus 4 thirds x. And you definitely want to clean that up first, distribute, before you start taking derivatives. So our area is going to become, when I distribute, 2 times 200 is 400 thirds x, minus 2 times 4 thirds is 8 thirds, x times x is x squared. So here's our area function. And again, if it's going to have a maximum, the only place it can have a maximum is at critical points. And that's going to be places where the derivative is either 0 or d and e. So next thing we need to do is find the derivative. So that's going to be a prime, the derivative of a. The derivative of 400 thirds x is just 400 thirds minus the derivative of 8 thirds x squared. When I bring down that 2 times 8 thirds becomes 16 thirds, and the power on the x goes down to 1. Whoops, sorry about that. So here's my derivative. Now the critical points are going to be wherever this derivative is 0 or d and e. And since this is a linear function, since we just have an x to the first power, it's never going to be d and e, but it will equal 0 somewhere. So that's what we need to solve next. So if I take 400 thirds minus 16 thirds x and set it to 0, I can add the 16 thirds over to the other side, and then to solve this I'm just going to multiply by the reciprocal 3/16 on both sides. So the 3's will cancel, and 400 divided by 16 is 25. So now we know what x is. Now what we want to do when we're showing that something is a maximum, that's our last step up here, this verify step. You want to prove that what you just found is actually the max or min that you're looking for, because remember, critical points could be maximums or they could be minimums. So who's to say that this 25 doesn't give me a minimum area? We need to show that it doesn't. We need to show that it gives a max. So this is where that second derivative test comes in very, very handy. This is probably the biggest place you'll use that second derivative test. What the second derivative test does is you find that second derivative. So if a prime was 400 thirds minus 16 thirds x, then a double prime would be, this goes to 0 because it's a constant, and the derivative of negative 16 thirds x is negative 16 thirds. Now here's what the second derivative test tells you. If your second derivative is negative, which this one is, at your x value, and in this case the second derivative is always negative no matter what x value we look at. So since this is less than 0, that means we're talking about a concave down function, which would look something like this. And the only kind of extremum that a concave down function could have is a maximum. So this shows that we have a max at x equals 25. Because if we're concave down and we have a critical point at 25, then the only thing it could be is a maximum. So this is our proof that we do have a max. Now last but not least, we want to make sure we're answering the final question. This question says, what are the dimensions? So we want to know not only x, but we also want to know y. So that's where this box comes into play. Once you've found out what x is, and we found out that x was 25, we can go right over here and we can let x equal 25 into this expression. So y becomes 200 over 3 minus 4/3 times 25, which is 200 thirds minus 100 thirds, which is 100 thirds. So our dimensions would be x equals 25, and we were talking about feet, and y would be 100 thirds feet. Okay? All right, so let's try another example. All right, the next example says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So again, a picture is very important here. So let's draw an open box with a square base. So we're going to have a square base, and then we have our box coming up like this. So if the base is square, that means its dimensions on the bottom have to be the same. So if I call this dimension x, then this would also have to be x. But it doesn't say anything about what the height is. So the height could be anything, so let's call it y. So here are my dimensions. Now let's talk about our objective function and our constraint equation. Remember that the objective is the thing that you're trying to either maximize or minimize. So look at your problem to see what quantity it is we're trying to maximize or minimize. And in this last sentence, it says we want maximum volume. So we want maximum volume. And what would be the formula for the volume of this particular box? Well, volume of a box is length times width times height. So that would be x times y, or x squared y. This is the quantity that we're going to want to take the derivative of. You always want to take the derivative of your objective, whatever it is you're trying to maximize or minimize. But right now, there's too many variables. We have an x and a y. So we need to eliminate one of those, and that's what the constraint is for. So the constraint is that fixed quantity or that number that they tell you in the problem that you have to maintain. And here, that's the surface area. It says the surface area has to be 108 square inches. So what would be the surface area of this shape here? Well, surface area is just the area of all your faces. Now think about the bottom here. The bottom, which you can't really see very well, is a square base. So its area would be x times x, or x squared. We don't have a face on the top because remember this was an open box. So there's no top, but there is a bottom, and its area would be an x squared. Now what about these side faces going around? Well, each one of those is a rectangle that's x on one side and y going up. X on one side, y going up. So their areas would be x times y, and there's 4 of them for all 4 faces. So the sides are going to be 4xy. So we've got our bottom, and we've got our 4 sides, and there's no top because it's open. So this is our surface area, and this needs to be that 108. So it's from this constraint that we're going to solve for one of the variables and then substitute that into our objective. Now you can see from this surface area equation that it's probably easiest to solve for y because there's only one of them. So I'm going to subtract that x squared over to the other side, and then I'm going to divide every single term by 4x. So 108 divided by 4 is 27, but we still have that x in the bottom. And x squared over an x reduces to an x on top with that 4 in the bottom. If you want, you can take that x that's in the bottom of our 27 and move it up to the top and make it a -1. That's up to you. And then this is like a 1/4 out front of our x. So there's what y equals. And now what we're going to do, substitute that in over here. So our volume equation will become x squared times 27x to the -1 minus 1/4 x. And always clean this up first. It'll just make taking that derivative much easier later on. So let's go ahead and distribute our x squared across. We'll get 27 x squared times x to the -1. You add exponents. So 2 plus -1 would be 1, or just an x. And then we have that minus 1/4. X squared times x is x cubed. So here's my volume equation. Next thing that I want to do is take the derivative, because you have to find those critical points in order to determine where your maximums could occur. So the derivative of volume, or v prime, is going to be 27 minus, when I bring down that 3, this becomes 3/4 x squared. Critical points are going to be wherever this derivative is 0 or d and e. Since this is quadratic, it's never going to become d and e, so I don't need to worry about that case. But it will be 0. So let's solve. I'm going to go ahead and add the 3/4 x squared over to the other side. I'm going to multiply by my reciprocal 4/3. And that's going to give me, when I reduce here, 3 goes into 27 9 times. 9 times 4 is 36. So I get 36 is x squared. And when I take the square root of both sides, I'll get a plus and a minus 6. But since we're talking about lengths here, x is a distance, we don't want the negative. So we want our x to just be the positive 6. Okay? Now, before we find out what y is, it's a good idea to verify that this 6 really is giving you a maximum and not a minimum or something else. So that's where that second derivative test comes into play. So the second derivative, v double prime, would be the derivative of this first derivative right here. The 27 goes to 0, and when I bring down my 2, -3/4 times 2 reduces to -3/2, and x squared becomes an x. Now this does have an x still in it, so at x equals to 6, when I plug that 6 in, this second derivative becomes -3/2 times 6, or -9. Which is less than 0. We want it to be a negative answer for the second derivative test, because if your second derivative is negative, that means you're concave down, which means that you have a maximum at the value that you plugged in. So this is our proof that we have a max at x equals 6. So now we need to find our other dimension. So let's go and find y by plugging in 6. And I'm going to take that x and move it back down to the bottom and put that 6 in the bottom. So it would be 27 over 6 minus 1/4 times 6. And when we simplify that, we can get 6 is divisible by 3. 27 is divisible by 3. So this is 9/2 minus 3/2, which is 6/2, which is just 3. So the y value is 3, therefore our dimensions are going to be 6 by 6 by 3. So 6 feet, or excuse me, inches by 6 inches by 3 inches. And there's our answer. Okay? All right, let's try another one. All of the examples that I'm showing you today are pretty standard, common examples that you typically see in your homework in your math textbook. So you'll probably be asked to do some very similar to these in your homework assignments. Okay, so the next one here says a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are each 1.5 inches. The margins on each side are 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So again, a picture here is key. So let's draw our piece of paper. Now this is the actual sheet of paper, but we have margins so that the actual print and the words are going to be on this inner rectangle. And the margins that we have are going to be 1.5 on the top and the bottom, 1.5 inches. So I'm going to use a decimal here, 1.5 inches from the top, 1.5 inches from the bottom. And the margins on the sides are 1 inches. So this is 1 inch from the right and 1 inch from the left. We have 24 square inches of print. And remember, the print is just on the inside of here. So the 24 square inches is a unit of measurement for area. So that means the area of this inner rectangle is the 24. And what we want to find out is what the dimensions of this big rectangle should be so that we use the least amount of paper. Now, least implies a minimum, so we want to use the minimum amount of paper, and that would mean the minimum area of this big rectangle. So we're trying to minimize the area of the big rectangle when the constraint is that the area of the small rectangle is 24. Okay, now we need some dimensions on here. So it's kind of your choice what you want to let your x and your y be. You can let x and y be the dimensions on the inside, or you could let x and y be the dimensions on the outside. Since I'm looking for the dimensions of the outer rectangle, I'm just going to let my x be this outside x and this outside y. Now based on that, we can get expressions for what these dimensions should be on the inside, because this x is that entire width going across. The inner dimension right here is that same x with 1 inch taken away from both sides. So that's going to leave me with x minus 2 on the inside. So that's that dimension right there. Similarly, y is this whole width or length going up and down. So the inside height going up and down is 1.5 taken away from the top and 1.5 taken away from the bottom. So that's taking away a whole amount of 3 inches total. So that means this dimension here is going to be that original y minus the 3 inches we're taking away due to the margins. Okay, so we've got all of our dimensions in there. Let's write down what our objective and our constraint are. So the objective, this is the thing that you want to maximize or minimize. We want the least amount of paper. Now least means minimum. So we want to minimize something. And what is it we're trying to minimize? We want the least amount of this big sheet of paper, which is its area. So we want to minimize the area of the paper. And that paper, the big rectangle, has as its area this x times this y. So the objective equation is just x times y. The constraint is that we have 24 square inches of print. The print is going on the inside here. So that's going to be the area of this inner rectangle, which has as its dimensions x minus 2 and y minus 3. So the area of this inner rectangle will be x minus 2 times y minus 3, that's length times width, and that area is forced to be 24. So we have our objective, we have our constraint, we're ready to start solving. Now before I can take any derivatives, I need to eliminate one of my variables here. So again, I'm just going to choose y. So I'm going to go to my constraint and I need to solve this for y. To do that, what I think is easiest is just to go ahead and divide both sides by that x minus 2 factor right away so that you get y minus 3 by itself. And then what I can do is just add this 3 over to the other side. So y equals 24 over x minus 2 plus 3. So there's what y is, and now I'm going to substitute that in up here. So my area becomes, instead of x times y, it's x times 24 over x minus 2 plus 3. And when I distribute, that's 24x over x minus 2 plus 3x. Now what we want to do next is find our critical points, which is where the derivative is 0 or d and e. So I need to take the derivative of this next. Alright, so derivative a prime is going to be, now this first expression here is a fraction, a quotient, so I'm just going to go ahead and use my quotient rule, which would be low d high minus high d low over low low. So the low is x minus 2. The d high, or the derivative of the top, would just be 24, minus the high, which is 24x, times d low, the derivative of the bottom is just 1, over low low, the bottom squared. And then we have to add to that the derivative of the 3x, which is going to just be 3. So this is our derivative, and I'm going to want to clean it up quite a bit here. So when I distribute, I'm going to get 24x minus 48 minus 24x over x minus 2 quantity squared plus 3. The 24x's cancel, so I get negative 48 over x minus 2 quantity squared plus 3. Now we want to know where this derivative is 0 or d and e. And in this example, it is possible for this to become d and e because we ended up with a fraction. So this is d and e wherever that denominator is going to become 0, which is at x equals to 2. So there is a critical point at 2. We also could have a critical point where this is equal to 0, so I need to do a little bit of solving to figure that out. And unfortunately, I'm running out of room over here, so let me see if I can squeeze it in over here. So I'm going to take my negative 48 over x minus 2 squared plus 3 and set that to 0. So if I add this whole fraction over to the other side, it becomes positive. And then I'm just going to multiply both sides by that denominator. Basically, I'm just cross multiplying. So I get 3 times x minus 2 squared equals 48. When I divide by 3, that gives me 16. When I take a square root of both sides, we get square root of 16 is either plus or minus 4, and then I would want to add 2 to that. Now if I used positive 4, then this will be 4 plus 2, which is 6. If I use the minus 4, negative 4 plus 2 is negative 2, and that would give me a negative dimension, so we don't want that. So we've got two critical numbers. We have 6 and we have 2. So at this point you need to figure out which one of these are the minimum that we're looking for. And you can do either the second derivative test or you could do the first derivative test. Both would work here. I'm going to go ahead and use my second derivative test because it's not that difficult to do based on what my first derivative looks like. Okay, so if we take a look at our first derivative here, we have negative 48 over x minus 2 quantity squared plus 3. Now the derivative of that, the 3 is going to go to 0, but to find the derivative of this first piece, it might help me to rewrite that as negative 40, whoops, sorry about that, negative 48, and then I'm going to move that x minus 2 up and make it become a negative 2 power. That's just going to help me take that derivative a lot easier. So then the second derivative would become, when I bring down this negative 2 times negative 48 is 96. And then I'm going to decrease the power by 1, so this becomes a negative 3, and the derivative of what's inside would just be 1. So this is just 96 over x minus 2 quantity cubed. So if I look at my critical point of 6 right here and I plug that in, 6 minus 2 is 4, and 4 cubed is positive, and 96 divided by a positive is going to stay positive. So at x equals to 6, this second derivative is greater than 0, which if it's positive, that means you're concave up. That implies that we have a min at 6. So that's what we want. Now what happens at that 2? Remember, we had a critical number at 2 as well. Well, the test actually fails at 2 because when you plug in 2, you're going to get a 0 in the denominator. So that second derivative doesn't exist. We need it to either be positive or negative to tell us something. But if we look a little bit more closely at our picture over here, let's figure out if 2 would actually work. If x was 2, then that would make this inside dimension here become 2 minus 2, or 0. And that means we wouldn't have any width here at all on that inside rectangle. So 2 is not going to be valid for us because it would make this inside print disappear. So the only solution we want is the 6. So last but not least, we know what x is, we just need to figure out what y is. So if I know that x is 6, I'm going to come up here and I'm going to plug in 6 for x. So y would be 24 over 6 minus 2 plus 3. So 24 over 4, which is 6, and 6 plus 3 is 9. So our dimensions are 6 inches for the x by 9 inches for the y. Okay? All right, let's try another example. This one is another open box problem, but this one is a little bit different. What we're going to do is we're going to create an open box by taking a rectangular piece of material that's 2 feet by 3 feet, and we're going to cut equal squares from each corner and turn up the sides. And then we're going to find the dimensions of the box of maximum volume. So first let's visualize how we're constructing this box. We're taking a 2 by 3 foot piece of material, and then we're going to cut out little squares from each of the 4 corners. And when you cut out those squares, you're going to be left with a piece of material that looks like this. And then to construct our box, we're going to fold along these little dashed lines. So our box, when I fold up these 4 flaps, is not going to have a top to it at all, but it's going to look something like that. Okay, so let's figure out what our variable is here. The question is, find the dimensions of the box of maximum volume. So we want the dimensions of this box over here. And what we're doing is we're starting out with a 2 by 3 feet of piece of paper, but they're not telling us how much we're cutting from each corner. All we know is that we're cutting out little squares. So the variable here is this little x that we're cutting out, and it's a square. So this would also be x, and all 4 of these squares are the same. So we're cutting out the same amount from each corner. So how does that reflect itself into this picture over here? Well, if you cut out an x, then that means this little distance right here is x. So when I fold that flap up, that becomes this height of my new box. Okay? This distance right here is this flap length, or this distance right here going across from here to here. And that distance is what we would have left over after cutting out our 2 x's from both of these sides. So we're taking away x from here and x from here, and we started with a width of 2 feet. So if I take 2 x's away from 2 feet, then that means what I'm left with is 2 minus 2x. Similarly, this dimension right here is this distance right here, which is whatever we would have left along here after taking away an x from the top and the bottom. So we started with a full length of 3, and then we're subtracting from that an x and an x. So we're subtracting away from 3 2 x's. So our volume of this box is length times width times height. So these three dimensions multiply together. Now you can multiply them together in any order you like, and I like to put the x first since it's a single term, and then you can do the other two in whichever order you like. Now what is it we're trying to do in this problem? We're trying to maximize volume. So this is the quantity that we want to find the maximum of. This is our objective. Now notice that it is already in terms of a single x. There's no second variable involved that we have to try and eliminate. So this particular example doesn't really have a constraint. It actually does. It's the dimensions that we were given initially and the way that we constructed this box. So the constraint has actually already been factored into how we figured out these dimensions. So we've already sort of used the constraint already. Okay, so here's our volume. We want to maximize it, and in order to find the maximum, we need to take a derivative. And you don't want to have to use a product rule if you don't have to. So I would recommend foiling this out first before you take the derivative. Now when I go ahead and FOIL here, you have three things being multiplied. So what I like to do is multiply this x across just to the first factor. You don't want to multiply it to both of these. You only want to use the x once. So when I multiply it to the first factor, we get 2x minus 2x squared. And I still haven't used this second factor, so now I'm just going to do FOIL. So we'll get 2x times 3, which is 6x. 2x times a negative 2x is negative 4x squared. Minus 2x squared times 3 is minus 6x squared. And a minus 2x squared times a minus 2x is a positive 4x cubed. Combining like terms gives me 6x minus 10x squared plus 4x cubed. And now we're ready to take our derivative. So v prime will be 6 minus 20x plus 12x squared. And this is just a nice quadratic equation, so it's never going to become undefined, so the critical points will just be wherever this is 0. Now to solve this, chances are you're going to have to use quadratic formula because I don't believe that this factors. So we would have to use quadratic formula. So that would just be x equals minus b, which is this 20, plus or minus b squared, or negative 20 squared, minus 4 times a, which is the 12, times the c, which is the 6, all over 2 times a, and the a is that 12, that coefficient of the x squared. Now I'll leave it to you to punch that into your calculator, but the two solutions that we get are approximately 1.274 and 0.392. They're both positive. So we have to think about which one could it be. You can either look back at your original problem and sort of maybe eliminate one of the choices right away, or you can take a look at your second derivative and look at it that way as well. If you look at your dimensions here, if x is bigger than 1, like this example right here, 1.274, when I plug that in, anything bigger than 1 is going to make this dimension go to 0 or become negative. So that's why this one is actually not going to be a valid solution. We need an x that's smaller than 1. Now let's verify that this 0.392 is actually giving us the maximum that we're looking for. So I'm going to take a second derivative. Derivative of 6 goes to 0. Derivative of negative 20x is negative 20. Derivative of 12x squared is 24x. And now we need to substitute in that 0.394. Or excuse me, 0.392. And when you substitute that in, you do end up with a negative solution. So this is less than 0 because we're taking a little more than a third of 24, which would be about 8, and that's going to be too small or to counterbalance the negative in front of that 20. So this is a negative result, which is good news for us because if our second derivative is negative, that implies that we have a maximum at 0.392. So there's our proof. Now all we have to do is finish finding our dimensions. So if x is 0.392, then we would want to substitute that 0.392 in for this x and also in for this x to get those two dimensions. And again, I'll leave that for you to plug into your calculator. But here's what we come up with. That height, which was the 0.392, that was our x. And then these are in feet. And then 2 minus 2 times 0.392 and 3 minus 2 times 0.392, those are going to give me 1.215 feet and 2.215 feet. So there are our three dimensions of our box. Okay? All right, next example. Find two positive numbers such that the product of the numbers is 192 and the sum of the first plus 3 times the second is a minimum. Okay, so here we don't need a picture at all. We can just kind of jump right in and start translating. Let's think about what our objective and our constraint are. So what do we want to do? We want a minimum, and we want the minimum of the sum of the first plus 3 times the second. We want to minimize that quantity. So it's not really an area or a volume or something like that. It's just an expression. We want to minimize the sum of the first plus 3 times the second. So if I call the first x, then I want to add x plus 3 times the second, so 3 times y. So it's that quantity that we're trying to minimize. What's our constraint? What's the number that they give me here? They tell me that the two positive numbers have a product equal to 192. Product means multiplication. So if I multiply my two numbers together, x times y, that needs to equal 192. So there's my constraint. So all we have to do now is eliminate one of our variables in our objective function by solving the constraint for either x or y. So I'm going to just go ahead and solve for y. So y is 192 over x, or if you prefer, you can move that x up and make it 192 x to the negative 1. And then we're going to substitute that in. So this becomes x plus 3 times 192 x to the negative 1, which is x plus 576 x to the negative 1. I don't have a good name over here for what to call this, but let's just call this our sum. So now that we have figured out what this sum is, next thing we want to do is take its derivative to find out the critical points. So the derivative of x goes to 1. When I bring down my negative 1, this becomes negative 576 x to the negative 2, which is the same as 1 minus 576 over x squared. So we need to know where this is 0 and where this is d and e. Since there's a fraction, it does have the potential of becoming d and e, and that would be wherever this denominator is 0, which in this problem would just be 0. Now I can rule that out right away, because if x is 0, then the product of 0 with any other number is never going to equal 192. So we know that this can't be the solution. So let's take a look at the other one. So let's take 1 minus 576 over x squared and set it to 0. So I'm going to add this fraction over to the other side. Then I'm going to multiply that x squared over, and then I'm going to take a square root of both sides. And that will be plus or minus, and the square root of 576 is 24. Now, it did say in the original problem that we were talking about positive numbers. So because of that, I can eliminate the negative and say that x is 24. Now let's verify that. So remember, our first derivative was this 1 minus 576 x to the negative 2. So the second derivative will be the derivative of 1 goes to 0, and when I bring down this 2, I'm going to get positive 1,152, and I'll get an x to the negative 3, which is like 1,152 over x cubed. So if we plug in 24 into that, we're going to get 1,152 over 24 cubed, which is obviously positive. And if your second derivative is positive, that means you're concave up, which means that you have a minimum. And that's what we wanted. So we have shown that we have a minimum at x equals to 24. So last but not least, we know what x is. We need to find the other number as well, which is our y. So to find y, we're just going to plug in 24 for this x, and 192 divided by 24 is 8. So my two numbers are 24 and 8. Okay? All right, next example. Find the point on the circle x squared plus y squared equals to 9 that is closest to the point 4, 5. So let's draw a picture here. X squared plus y squared equals to 9 is a circle centered at the origin with a radius of 3. So it's going to look something like this. And 4, 5 is going to lie somewhere outside of that circle. So we're looking for the point on this circle that's closest. And you can kind of visualize where it would be. We want this distance to be as small as possible. So this point, whatever it is, I'm going to call it x, y. And we know that this point is 4, 5. Okay, so what is it that we're trying to do here? If we want this distance to be, or if we want this point to be as close as possible to our circle, then that really means we want this distance between these 2 points to be as small as possible. In other words, we want them to be minimized. So we're trying to minimize the distance between our 2 points. And our 2 points are 4, 5 and this x, y. Now this requires knowing the distance formula, because if you want the distance between 2 points, you need a distance formula. So the distance between 2 points is the square root of the difference in the x's. So my two x's are 4 and x. I'm going to subtract x minus 4, and that's squared, plus the difference in the y's. So y minus 5. It looks very similar to that Pythagorean theorem. And along those lines, if we want to minimize our distance, notice this distance formula has this really nasty great big square root, which is going to make taking a derivative quite tedious and yucky to do. So one thing you can notice is that if you're minimizing the distance, that's going to happen at the same point, x, y, wherever the distance squared is minimum. So one little trick that we tend to do in problems like these is we square the distance to get rid of that yucky square root, and then we minimize this distance squared instead. And that just makes our life a little bit easier. Now notice this was our objective, because this is what we're trying to minimize. Where's our constraint? We have 2 variables here, and we can't take a derivative of this until we eliminate one of those variables. So the variable y or x, whichever one we choose to get rid of, needs to get eliminated using our constraint. What is the constraint? Well, it's the fact that this point x, y has to lie on this circle, and we know what our equation of our circle is. So this equation of our circle is actually our constraint. That's what is forcing us to be true. We have to have that x and y must satisfy that equation. So if we take our constraint, x squared plus y squared equals to 9, and we solve it for y, I could subtract the x squared over to the other side and then take the square root. Now this is technically a positive or a negative square root, but you can clearly see from our diagram here that the point that's going to be closest is the point that's in the first quadrant, and that's going to happen when your y is positive. So I only need to worry about using the positive square root. So here's what y is, and now I can substitute that in right here to eliminate my variable. Okay, so this is pretty messy, but now what we're going to need to do is take the derivative of this distance squared. So I'll write that as distance squared prime. And you could FOIL this stuff out, but I don't think it's going to get a whole lot cleaner doing that. So I'm just going to leave it as is and use my chain rule and my power rules and all that good stuff when I take my derivative. So the derivative of this first piece needs a chain rule. I'm going to bring down the 2, subtract 1 from the power, leave what's inside the same, and multiply by the derivative of what's inside, which would just be a 1. So that piece is done. Now I'm going to do the same thing on this second piece. Bring down the square, what's inside stays the same, reduce the power by 1, but then I need to multiply this by the derivative of what's inside. And this square root of 9 minus x squared is really, if you want to change that square root to a 1/2 power, then it might make it easier to see what the derivative of this inside piece would be. I have to take the derivative of this part first, so I bring down the 1/2. When I subtract 1 from the power, 1/2 minus 1 is negative 1/2. And then don't forget to multiply this by the derivative of what's inside. The derivative of 9 minus x squared is a negative 2x. And then the derivative of the minus 5 just goes to 0, so I don't need that at all. So here's all the pieces of my derivative. Now we need to clean it up as much as we can. So I'm going to go ahead and distribute my 2 across. I'll get 2x minus 8. This 1/2 will cancel with one of my 2, so let's just cross off that 2. And what we'll have here is this negative 2x, so let me actually make this a minus. So I have this minus 2x, and I have it being multiplied by this square root of 9 minus x squared minus 5. And then I have this other 9 minus x squared to a negative 1/2. That's in the denominator because it's a negative, and I'm going to put it back under a radical. So here's what my derivative is starting to look like. So what I'm going to get next is a reduced fraction. I'm going to kind of rewrite this just a tad here. I'm going to get 2x minus 8, and then I'm going to have this minus 2x out front, and what I'm going to do is in parentheses here write out what this becomes, and we can break that up into 2 fractions. This reduces to just a 1 minus this stays 5 over square root of 9 minus x squared. And the reason I'm doing it this way is so that when I distribute this minus 2x across, I'll get these 2x's to cancel, and then this becomes a positive 10x over square root of 9 minus x squared. So we get a little bit of cancellation going on, and we get negative 8 plus 10x over square root of 9 minus x squared. So there's our derivative. Critical points are going to be wherever this is 0 or d and e. Now the denominator does become 0 at plus and minus 3, but in the context of our question that would be these points right here and right here, and you can see that those clearly aren't going to be the closest points to 4, 5. There's got to be one closer. So I'm going to rule those out as options, and I'm just going to worry about the 0 case. So if I go and I set this to 0, I'm going to add that 8 over to the other side. Then I'm going to cross multiply that square root over to the other side. And then we need to square both sides to get rid of that square root. So this becomes 100 x squared equals 64 times 9 minus x squared. Got 100x squared equals 64 times 9 is 576 minus 64x squared. When I add that 64x squared over to the other side, I get 164x squared equals 576. Divide by 164. And you can do some reducing there if you like. But eventually we're going to need to take a square root of both sides. And I would just go ahead and get a decimal for that because it doesn't come out to be a nice perfect square. And this, I'm only going to use the positive because we're in quadrant 1. So the positive square root equivalent of this decimal is approximately 1.874. Okay, so that's what my x would be. Now at this point what we would want to do is check whether or not this is our maximum or our minimum. So we can do a second derivative test. On this particular example, remember our first derivative down here, it's kind of messy because you've got that big fraction with radicals in it. It's going to be a little bit messy to do that second derivative. So as an alternative to doing the second derivative test, you can show that this is going to be our minimum by using the first derivative test. And remember how that works. That's just using your number line. So if we put 1.874 on our number line and we test into this first derivative, a number to the left and to the right of it, we'll see what sign changes occur. And what we want to happen, if this is going to be a min, is a negative on the left and a positive on the right. So for example, if I plugged in 0, that's obviously going to make this whole fraction go to 0 and I would just get -8. So this will be minus. If I tried something like 2, then I'm going to get 20 divided by 9 minus 2 squared is 4, so 20 divided by square root of 5. And then when I subtract 8 from that, you can plug that in your calculator and see that it actually does end up being a positive. So I'm doing that a little bit quickly, but it's really just a calculator issue. Plug it in and verify your signs, and because this goes down on the left and up on the right, then that does prove that we have a minimum. And that's what we wanted. We wanted to minimize our distance. So first derivative test or second derivative test would be a way to verify. Finally, we know what our x is, so we go back to our box over here to find out what y is. And again, that's just a calculator issue. You're going to plug in this decimal and simplify, and what you end up with is y is approximately 2.343. So the point that minimizes this distance is 1.874, 2.343. And that seems realistic, right? If you look at your picture here, we want to be somewhat close to 2 for the x and somewhat close to 2 for the y. So that looks like we are about on the right track. Okay, so this one had a lot of messy algebra in it with some solving. Just kind of brute force, you have to work your way through it and eventually try to simplify that derivative as much as you can to make the solving become a little bit easier. Okay? All right, let's try another one. This is the infamous can problem. So here, if we have a closed tin can of volume 60 inches cubed, it's to be formed in the shape of a right circular cylinder. We want to find the base radius of the can if the least amount of tin is to be used in its manufacture. Okay, so we've got a right circular cylinder. It's going to have a base radius, and the other dimension that's important here would be the height, which we'll just call h. So let's think about what our objective and our constraint are. Now the objective, what is it we're trying to maximize or minimize? We want the least amount of tin. Now the tin is what makes this can, and that's going to be all that surface area that we're talking about. So we want to minimize, because we want the least amount, we want to minimize surface area of this can. So what would be the formula for surface area of a right circular cylinder? And you can look these formulas up. They're usually in the front or back cover of your textbook. But for a right circular cylinder, that's just going to be the area of the top and the bottom, which are both circles. So area of a circle is pi r squared, and we have 2. So 2 pi r squared for the top and bottom base. And then if you were to slice this can down the side and unfold it, it's going to basically form a great big rectangle, where the height of that rectangle is just our h, and the length of that rectangle turns out to be the circumference of our circle, which is 2 pi r. So 2 pi r times h would be our sides. So the surface area formula is 2 pi r squared plus 2 pi rh. So that's what we want to minimize. And it has an r in it and an h in it, so we need to eliminate one of those variables. Therefore, we need a constraint. So what's the number that they give me in this problem? 60 inches cubed, which is our volume. So our constraint is going to be our volume. Well, what's the volume formula for a right circular cylinder? Well, that's just the area of your base times your height. And the base area is a circle, so that's pi r squared times the height h. So volume is pi r squared h, and that's what needs to equal 60. So it's easiest, I think, to solve this for h by just dividing by pi r squared. So h is 60 over pi r squared. And then we can take that and substitute that in up here. So my surface area becomes 2 pi r squared plus 2 pi r times 60 over pi r squared. So simplifying that a little bit first, we're going to get the pi's cancel and one of the r's cancel. 2 times 60 is 120, and we'll still have an r in the bottom. And you can move that r up to the top and make it a -1 if you want. So now we have our surface area. Let's take the derivative to find those critical points. So the derivative of 2 pi r squared, remember 2 pi is a constant, so when I bring that square down, it's going to become 4 pi, and the power on the r just becomes 1. Then the derivative of 120r to the -1 becomes -120r to the -2. So this is 4 pi r minus 120 over r squared. And this is 0 or d and e. It will become d and e when that denominator is 0, which is going to happen if r is 0. But if the radius is 0, we won't have a can. So that's not going to be feasible for this problem. So this can become 0 if we take our 4 pi r minus 120 over r squared and set it to 0. I'm going to add that fraction over to the other side, and I'm just going to cross multiply again. I'm just solving that proportion by multiplying across by r squared. So this becomes 4 pi r cubed equals 120, and when I divide by 4 pi, it's going to give me r cubed equals 30 over pi, and if I take the cube root of both sides, then r will be cube root of 30 over pi, which is approximately 2.1216. Now to verify this, I'm going to go back up here to my first derivative, and taking a second derivative isn't too hard to do here. So I'm going to use my second derivative test. The derivative of 4 pi r would just be 4 pi. And then when I bring down my -2, this becomes positive 240, and the power on the r becomes a -3, which I could put in the bottom. Now don't waste a lot of time here, because if you know that r is approximately positive 2.1216, when you plug that in, that's going to stay positive, and all the rest of these numbers are positive as well. So this second derivative is going to be positive, which means we do have a min at r equals 2.126. Okay, so we've proved or verified our minimum. This particular question is actually only asking us to find the base radius, but sometimes and usually you do want to know the height as well. So if you wanted to know the height, you would just go up here and you would plug in that cube root of 30 over pi, or you could use the decimal value as well, and you're just going to get a decimal for that h, and it's about 4.243. So our dimensions here would be our radius, which is approximately 2.1216, and these are in inches, and our height is about 4.243 inches. Okay? All right, the next example is a very, very common question. It's called the Norman window problem. And what we're trying to do here is have a Norman window that consists of a rectangle surmounted by a semicircle. So it's just the shape of this window. It's called a Norman window whenever you have a rectangle with a semicircle mounted on top. Okay? If the perimeter of a Norman window is to be 32 feet, determine what should be the radius of the semicircle and the height of the rectangle such that the window will admit the most light. So we're looking for the radius, which would be here, and this height h. Let's figure out what our objective and our constraint are going to be. So our objective, what is it we're trying to maximize or minimize? Here what we're trying to do, it's a little bit not as obvious here, but it says we want the window to admit the most light. So most means maximize. What is it we're trying to maximize? Well, if we want to admit the most light, the only way that's going to happen is if that window is big, and the size of the window corresponds to its area. So we're trying to maximize the area of that window to let in the most light. So our objective is to maximize area. So we need to figure out a formula for the area of this shape. Now it consists of two pieces, the rectangle and the semicircle. So let's figure out the area of the rectangle first, and then we'll do the area of the semicircle. Now since the radius is up here, that means that this distance down here would be 2 radii. It's 2 r's. So the area of this rectangle piece would be this width times this height, or 2r times h. So that's the area of the rectangle part. Now let's factor in the area of the semicircle. Area of a circle is pi r squared, but we're not using the whole circle, we're using half of it. So the area of half of it would be 1/2 pi r squared. So there's our area. It has too many variables in it, so we need a constraint. And what we're told is that the perimeter of this Norman window is 32 feet. Now the perimeter would be sort of like the trim that would go around. So this distance down here, which we already know, is 2r, plus this trim here, and we have the same amount on this side, so that would be 2h's, plus this trim around the outside. And that corresponds to circumference, but it's not the circumference of a whole circle, it's the circumference of half a circle. Now remember, circumference of a circle formula is 2 pi r, so half of that would just be pi r. So we need to factor in that as well. And that whole perimeter is restricted to 32 feet. So there's our constraint. Since I have just a single h in my area formula, and I only have the one h term in my perimeter, I think it would be easier to solve for h here. So I am going to leave 2h where it is, and I'm going to subtract the 2r and the pi r over to the other side, and then I'm going to divide everything by 2. So h becomes 16 minus r minus 1/2 pi r. And now I can take that h and substitute it in up here. So my area becomes 2r times 16 minus r minus 1/2 pi r plus 1/2 pi r squared. And let's simplify. So we'll get 32r minus 2r squared minus the 2 and the 1/2 will cancel, so I'll get pi r squared plus half a pi r squared. Now these are actually like terms. You've got a -1 pi r squared plus a 1/2 pi r squared. So -1 plus a half is -1/2. So if we combine those, it'll be a -1/2 pi r squared. So there's our area, all nice and cleaned up. Now we're ready to go ahead and find our critical points. So area prime will be 32 minus derivative of 2r squared is 4r. And when I bring down this 2, it'll cancel out the 1/2, just giving me a minus pi, and the power on the r goes down to 1. Now this is actually a linear equation because it's just r to the first power. So it will never become dne, but it will equal 0. Now I have two r terms, so let's get those together on the right side of the equation by adding them both to the right side. And since they're both to the first power, I can just factor out that r, and that'll leave me with 4 plus pi, and then it becomes just a matter of dividing to solve for r. So r will be 32 divided by 4 plus pi. So now we know what r is. To verify it, I'm going to take a look at my second derivative. Here was my first derivative. The 32 goes to 0. The derivative of -4r is -4, and the derivative of minus pi r is just minus pi. There's no r there at all, so this is always a negative number, which means this is always concave down, which means we have a max, and that's what we want. We wanted to maximize our area. So this is our proof that we've found our max. And last but not least, we just need to find the other dimension, the height. So we're going to go over here, and we're going to let r be this 32 over 4 plus pi. Now you can get a decimal for that if you like. I'm going to try to do this exactly for this problem just to show you. So when I go to simplify here, we're going to have 16 minus 32 over 4 plus pi minus 2 goes into 16, or into 32 16 times, so this will be 16 pi over 4 plus pi. And I just need to get a common denominator here of 4 plus pi. So that means since the 16 was essentially over a 1, I have to multiply that 16 by 4 plus pi on the top and the bottom to make it equivalent. So I just got a common denominator there, and then these two fractions already had the common denominator, so I can just use their numerators unchanged. And when I distribute, I'm going to get 64 plus 16 pi minus 32 minus 16 pi. So the 16 pi's cancel, and 64 minus 32 is 32 again. So what this shows us is that y is also 32 over 4 plus pi. So our dimensions are going to be that the radius is 32 over 4 plus pi, and our units here were feet, just double checking there, and our height will also be 32 divided by 4 plus pi feet. Okay? All right, our last example. Our last example involves a little bit of trigonometry. Okay, here we have the cross sections of an irrigation canal are isosceles trapezoids, of which 3 of the sides are 8 feet long. Determine the angle of elevation theta of the sides so that the area of the cross section is maximum. So we're talking about an isosceles trapezoid where 3 of the sides are 8 feet long. So let's draw that. So here's what a trapezoid looks like, and to be isosceles, these have to match, and actually it tells me that 3 of the sides are all 8, so all 3 of those are 8. This longer side is obviously not going to be 8. And we want the angle of elevation theta so that the area of this cross-sectional shape, which is this trapezoid shape, is a maximum. So our objective is we want to maximize the area of this cross-section. And they're telling me that these cross sections are these shapes. So really what we're just trying to do is maximize the area of this trapezoid. Okay, now in order to find the area of a trapezoid, you need to know the formula for area of a trapezoid, and that's 1/2 the height times base 1 plus base 2. Now our base 1 is this 8. This bottom base down here we don't know yet, and we don't know our height. So let's draw in our height here, h. And notice that if I drop this perpendicular down as well, then that means this distance here is 8, and these two distances, this one I'll call x, and this one also is x. Those are equal because this was an isosceles trapezoid, so the angles on both sides are the same. So this base 1 is the 8, the base 2 is going to be 8 plus these two x's, whatever they happen to be. Now, we don't want to create all these extra variables, so this is where the trigonometry comes in. We have a nice little right triangle right here. So based on some trigonometry, we can get some relationships for what h and x are equal to in terms of theta. So let's start with h. H is opposite angle theta. And if I use that 8 over here, which is the hypotenuse, which trig function refers to opposite and hypotenuse? That would be the sine function. So we know that the sine of theta is h over 8. If I cross multiply that 8 to the other side, then that tells me that this height, h, is 8 sine theta. So now we know what to use for h. Now let's find out what this x is. So x is adjacent to the angle theta. So which trig function uses the adjacent side and the hypotenuse? That's cosine. So cosine of theta is the adjacent side x over the hypotenuse 8. And if I cross multiply, that tells me that x is 8 cosine theta for that total. So we know that this is 8 cosine theta, as is this one. So we're ready to write out our area formula. Our area formula, remember, is 1/2 height times base 1 plus base 2. And in this problem, our height h was 8 sine theta. Base 1 is this upper base, which has a length of 8, plus base 2 is this lower base, which is this middle 8 plus 2 of these 8 cosine thetas. So that would be a total of 16 cosine thetas. So we have the 8 from the middle plus the 16 cosine thetas on the sides. So there's our area formula. It only has one variable in it, theta, and that means we don't need a constraint because we've actually already factored in the constraint being the shape of that isosceles triangle and using those trig functions. So the constraint was built in already. Now let's clean this up a little bit. Half of 8 will be 4, so this is 4 sine theta, and 8 plus 8 will be 16. And let's go ahead and distribute, so I get 64 sine theta plus 64 sine theta cosine theta. So there is our area. Now we're ready to find our critical points, so we need a derivative. So the derivative of area, A prime, is going to be the derivative of 64 sine theta. 64 stays there, and the derivative of sine theta is cosine theta. Plus, now for the second piece, be careful here. This is sine theta times cosine theta. So you have to use a product rule here. Now what do you do with that 64? I kind of group it together with the sine. So my first function will be this 64 sine theta times the derivative of the second function. And the derivative of cosine is a minus sine. So there's first times derivative of the second plus the second, which is that cosine, times the derivative of the first. And the derivative of 64 sine theta is 64 cosine theta. Now let's clean it up. So we have 64 cosine theta minus 64 sine squared theta plus 64 cosine squared theta. Okay, now when I work with this, it's usually beneficial when you're working with trig equations because we're going to want to know where this is 0. It never becomes D and E because sine and cosine are always defined. So to find out where this is 0, we're going to have to solve this trig equation, and usually that's easiest if you're only dealing with a single type of trig function. We have sines and cosines going on, so it's probably a good idea to eliminate this sine squared function so that I can rewrite everything in terms of cosines. And in order to do that, I'm going to use an identity. So instead of sine squared, remember that sine squared plus cosine squared equals 1. Therefore, sine squared theta is 1 minus cosine squared theta. So I'm just trying to eliminate that sine function. And now if I distribute again, we get minus 64. We get a plus 64 cosine squared theta plus another 64 cosine squared theta. So this is going to become a quadratic equation. 64 cosine squared plus 64 cosine squared is 128 cosine squared theta. And then I'm going to put this 64 cosine theta in the middle and my minus 64 on the end. If you want, just to make the numbers a little bit easier here, you can divide everything through by 64. So this is 2 cosine squared theta plus cosine theta minus 1. And that will factor, because it's like a trinomial. If we have 2 cosine theta times cosine theta, and a 1 and a 1, let's make the 2 a plus and the 1 a minus, and we'll get a positive middle term. So when I set these to 0, I'm going to add the 1 and divide by 2. We need to know where is cosine theta equal to a half. And keep in mind, based on my shape here, that this theta is obviously going to be less than 90 degrees. So we only need to come up with a theta that's in quadrant 1. So what angle in quadrant 1 gives us a cosine value of a half? Well, that's the same as 60 degrees or pi over 3. So that's that solution. And then this one, if I subtract that 1 over to the other side, where does cosine of theta equal to negative 1? Well, that's going to be at pi. And that obviously is bigger than 90 degrees, so we can exclude that as a possibility. Okay, so then to finish it off, we would need to do a little checking to verify, and on this one, since our first derivative was kind of a mess here, I would probably recommend just using the first derivative test, making a number line. So if you take your pi over 3 and put it on a number line, and we go to our first derivative, which cleaned up was right here. And then we would need to plug in something to the left of pi over 3 like 0. If I plug in 0, cosine of 0 is 1, so this is 128 plus 64 minus 64, that's going to be 128, so that's positive. And then if I pick something to the right of pi over 3 like pi over 2 or 90 degrees, cosine of pi over 2 is 0. So this would go to 0, this would go to 0, and we would get negative 64. So that'll be minus, which means we're going up on the right and we're going down on the left. And that's what we wanted. We wanted to maximize this area of this cross section. We wanted maximum area. So this is our proof that we have a max at pi over 3. And our final solution was just to find this angle of elevation theta, which we just did. So our angle theta needs to be pi over 3. All right. We just finished a tough section on optimization problems. That concludes our video lecture. Good luck.